Okay, question 1a, part 1. State the main interaction when an alpha particle is scattered by a gold nucleus. Here, the main force that's causing this interaction from our alpha particle, which is a collection of protons and neutrons, and our gold nucleus, which again is a collection of protons and neutrons. The net charge of both of those is positive, so therefore we're getting electromagnetic, okay, or Coulomb, specifically repulsion. Okay, so interaction of like charges called Coulomb repulsion. Part 2, gold 4 is replaced. Okay, explain whether or not the scattering distribution of the monoenergetic alpha particles remains the same. If we've got the same isotope, Z must stay the same. Okay, the number of protons in there stays the same. If Z's the same, therefore net charge remains the same. As mentioned previously, it's the Coulomb repulsion that's causing that force to happen. So if the net charge is the same, the Coulomb repulsion is going to be the same. Therefore, force is the same as Z unchanged. Therefore, distribution unchanged. Okay, distribution is unchanged or remains the same. For 1b, we've got a graph of R against A from different experiments, different scattering experiments, and it tells us the relationship R equals R naught A to the third, something that we're given in our data book. It's got use information from the graph to show that R naught is about 1.4 times 10 to the minus 15. Okay, we'll just move down. We'll just do it under here. Okay, so we're going to use this equation here, R equals R naught A to the 1/3. If we're looking for R naught, we need to rearrange that. Okay, circle, that's what we want. To rearrange that's quite simple. We're just going to divide both sides by A to the 1/3. Okay. So we're doing this quite explicitly. A to the 1/3 over A to the 1/3 cancels out, gives us 1. Let me just remove that there. Okay, so we end up with R naught equals R over A to the 1/3. The reason we have to use the information from the graph is it's looking for us to infer a value of R and a value of A to put in there. Okay, so let's work with a nice easy number that we've got there. So we'll follow along from 8. Excuse the lack of a ruler. Nice and convenient. Work with numbers that are on the main lines, and we've got R equals 8 times 10 to the minus 15. Make sure we're using the scale on the axes. Divided by 175 equals R naught. Okay, if we type that into our calculator, we get a result coming out as 1.43 times 10 to the minus 15 meters. Okay, that's approximately equal to 1.4, so we're on the money. Moving on. Part 2, show that the radius of a 5123 V nucleus is about 5 times 10 to the minus 15. Okay, so I'll just scroll back up here. We're going to be using our relationship with our value that we've just worked out before to work out the radius. So our relationship, I'll write this down again, R equals R naught A to the 1/3. And the value we just worked out was R naught equals 1.43 times 10 to the minus 15 meters. Okay. Remember, the layout, the way we write our sort of atoms is like that. So our A number's at the top. So A in this case is 51. Okay, so we end up with R equals 1.43 times 10 to the minus 15. Remembering, although we're writing that, we're actually going to want to carry on and use our full value from our calculator to make sure we're not getting any rounding errors, times 51 to the 1/3. Okay, and that comes out, gives us a value of 5.3 times 10 to the minus 15. Remember our units, meters. Okay, again it says it's about 5 times 10 to the minus 15, 5.3 times 10 to the minus 15. That's right. Okay. Next question, C. Calculate the density of that same nucleus. State an appropriate unit for your answer. Okay, this is actually quite simple stuff. Going back, density, so the symbol rho is mass divided by volume. Okay. The mass is just going to be A. Let's move over here because that makes sense. Is A times the mass of a nucleon. So A is the total number of nucleons, so times the mass of a nucleon, so 1.67 times 10 to the minus 27 kilograms. Okay. Our volume is going to be the volume of a sphere. Okay, we're going to assume it's a sphere of radius r. Let's put it up here. We've just worked out the radius here, so we're going to be using that. The volume of a sphere is 4/3 pi r cubed. Okay, so if we put that in, we should get out 51 times 1.67 times 10 to the minus, sorry, sphere, 27 divided by 4/3 pi, one answer above, remembering to account for any rounding errors, it's a minus 15. Remembering to cube that as well. So if we type that in, bit of a longer one here, we should get out okay, it should get out 1.4 times 10 to the 17. Okay. Volume is going to be meters cubed, so our unit is going to be kilograms per meter cubed. So kg m to the minus 3. Okay. Which for 3 marks isn't actually that bad. So that's quite nice. Question 2 talks about half-life of carbon, effectively looking at carbon dating. Okay. Calculate the radioactive decay constant in years to the minus 1 of carbon-14. This is quite straightforward. This is using the lambda. So, the decay constant is ln2 divided by t12. Okay, so we can literally just chuck those numbers in there, and then we come out with a decay constant equal to 0.693 divided by 5740. Okay, notice the question says in years, and it's looking for a decay constant in per years, or years to the minus 1. So we don't need to change anything there, we don't do anything fancy with that. And that comes out as 1.21 times 10 to the minus 4 years to the minus 1. Okay, quite straightforward. It's a 1 mark question. A piece of wood taken from an axe handle found to have archaeological site as that many times, 0.375 times as many carbon-14 and an equal mass of living wood. Calculate the age of the axe handle in years. Okay, so this is going to be using our I'm going to do it as x equals x naught e to the minus lambda t. Okay, our exponential thing. In this case, we're looking at the number of atoms. Okay, so we're going to use n equals n naught e to the minus lambda t. Okay. We are then going to put those numbers in. So we're going to get n over n naught, okay, equals e to the minus lambda t. Taking logs of both sides, I haven't left myself a lot of room here. Okay, we're going to get ln n over n naught equals ln e to the minus lambda t. Using our log rules, we know that we can bring this bit down to the front. Okay, and we end up ln n over n naught equals minus lambda t. Log e, natural log of e is just 1, so we end up with that. Okay, can then work out t, as I'm just going to move this down here. T equals 1 over minus lambda ln n over n naught. Plug in the numbers in. Okay, we're going to get 1 over minus our answer from before, so minus 1.21 times 10 to the minus 4. Okay, times log. Now the ratio of n to n naught is actually going to be that 0.375. Okay, so if it was 0.375 times the original amount, then it's just going to be n is equal to, effectively, sorry, I'll write this up here, n is equal to 0.375 n naught. Okay, so those, the n naught would cancel in both cases. So we can just write in log of n over n naught is 0.375. And that comes out giving a time of around 8,100 to 8,200. Let me just double check that. 1.21 times 10 minus 4 times log. Yeah, 8,100. 8,100 years. Okay, so it's a 3-mark question there. Again, they haven't given you a lot of room, but that's quite a nice 3-mark question. B, suggest why the method of carbon dating is unlikely to be reliable, or actually unreliable, if the sample is less than 200 years old or more than 60,000 years old. Okay, so it's quite quite important to think about where the sort of the idea of carbon dating comes from and why it's useful. Sort of looked at here, we're using that decay constant. Okay, we're using the decay constant here, which is obviously related to the half-life. With the half-life of carbon, so the time taken for it to half is that many years, 5,740 years. If we're looking at something that's only 2 years old, it's just too short a time. Okay, just far too short a time for any measurable change in activity to happen. If we're looking at something that's 60,000 years old, we're now getting to the point where we've lost so much of that carbon originally, it's going to be really difficult to actually detect the difference between that and the background radiation. Okay, so the normal radiation we've got emitted from things like solar radiation and argon gas. Okay, so these are basically at the extremes, effectively. So this is too small, and that's too large, or too long, really. Okay, so in this case, it's a too small drop or change, too small to measure, accurately measure. Okay, and too long or activity would be comparable or hard to distinguish from background. Okay. Question 3. Unfortunately, this is across 2 pages, but we'll just go with it. Age of an ancient boat may be determined by comparing the radioactive decay of carbon-14 living wood to the ancient boat. Okay, so again, we're back onto the carbon dating question. Okay, so what is meant by the decay constant? Okay, it's quite a straightforward question. So we're just looking at the probability of decay per unit time. Okay, so it's basically sort of how likely it is that it's going to decay in a given amount of time, or sort of fraction decaying per sec. Okay, we prefer to talk about per unit time because obviously we have decay constants in years, etc. So, for B, we're calculating the half-life of carbon-14 in years, given it significant figures. Okay, so again, we've got 1 year. They've given it there in seconds. Okay, the reason they've given us that in seconds is because our decay constant, have a look at this, is in seconds, and they've asked for it in years. Okay, so that's why we sort of earn in the 3 marks this, because we're getting a conversion there. Okay, so again, we're going to use T half equals ln2 over lambda. Okay, we chuck our numbers in. If we get our T half in seconds, that'll be 0.693 over 3.84 times 10 to the minus 12. Okay, so that's what it is. That's what it is in seconds. If we want to convert that into years, we then want to divide by 3.15 times 10 to the 7. Okay, so we want to work out how many years that number of seconds is. Okay, and that comes out as 5730 years.